Okay, let's talk more about this ideal gas. Let's do ideal gas relations. Okay, ideal gas relations. And so we know for an ideal gas, it's only a function, that the properties are only a function of temperature. Temperature alone changes the internal energy or the enthalpy. So we have internal energy is a function of temperature. Okay. Now, we also can say that now that the specific heat at constant volume, which is a function of temperature, is going to be equal to du over dt. Now we don't have to worry about, it's just a function of temperature, so we can just use a full derivative. We don't have to use a partial derivative, just a full derivative here. Okay? Now, let's separate the variables here. We can say that du is equal to c sub v, which is a function of temperature, times dt. Now notice there I'm trying to say c sub v is a function of temperature. Don't get confused. People all the time say that c sub v times temperature. No, I'm trying to indicate it's a function of temperature. It changes with temperature. All right. So if we do this and we separate variables, now let's integrate. Okay, that's where our calculus comes in. So we're going to integrate this from 1 to 2 of du, and this is going to go from 1 to 2 of c sub v dt. And what are we going to get here? We're going to get u2 minus u1, or the internal energy 2 minus internal energy 1, is going to be equal to the integral from t1 to t2 of c sub v t dt. Now this, what I just showed you in the tables, this is what the tables do. The tables that I show you do this integral for you from some reference internal energy, and they give you that value. They say, okay, here's how specific heat changes for air over temperatures, and we're going to go from some 0 to temperature 290 Kelvin, and I'm going to show how that works, and I'm going to give you a value. Let's just say the temperature at 0, the internal energy at 0 is 0, and so I'm going to give you what the internal energy is at state 2, and I'm going to put it into that chart. So I'm going to give you, if I do this integral, I'm going to show you what the internal energy of 290 is. So that's how we create those tables. So you don't have to do all that integration. You don't have to worry about that at all, because the tables provide that for you. But there are times when you don't want to use the tables, and you want to just say, okay, I know, because I've dealt with this a little bit, that the specific heat doesn't change too much over a range of numbers. So let's say if we assume that the CV is constant over our temperature range. Okay, so if CV is constant, here's what happens. Now our integral that we have there, u2 minus u1, now over our temperature range, we can take CV out of the equation. It's going to be CV times, now it's just dt. So it's going to be T2 minus T1. Okay, so if we assume that specific heat is constant, now we can replace u2 minus u1 with CV T2 minus T1, or CV delta T. Okay, that's important. That's important. And similarly, we say that C sub P, which is now a function of only temperature when we're talking about ideal gases, is equal to dH over dt, the change in enthalpy over the change in temperature. And so we can separate values. dH is equal to C sub P, it's a function of temperature, times dt. And we can integrate that from 1 to 2 and from T1 to T2. And we're going to get that the enthalpy change, H2 minus H1, is going to be equal to, from T1 to T2 of C sub P, it's a function of temperature, times dt, and this is what's in the tables. This is the equation, the calculation the tables do for us, and nicely work it out. But if we assume that over the range of temperatures from T1 to T2, that our C sub P is relatively constant, so assuming C sub P is constant, we get that H2 minus H1 is equal to C sub P times T2 minus T1. Okay? And so these are the two equations that I want to make sure that you understand. If the problem statement indicates that you should follow an ideal gas model, the first thing that you want to do is look up values in the tables. Why? because we have taken into consideration the specific heat changes with temperature, and they've gotten really, really good values. Okay, we've already gone away. Here is our perfectly correct answer. We've gone slightly away from it, saying now we're doing an ideal gas model, and now we're going to use these tables, which can give us really, really good numbers. Okay, now let's just say we want to say, all right, but now I'm going to assume that this specific heat is constant. Now I'm given another slight error in my calculation, very slight error in my calculation, depending upon the range of temperatures I'm working with, and I can now go with this ideal gas constant specific heat model. So we are going to say here, ideal gas, constant specific heat, we're going to say that delta U is equal to C sub V times delta T, and delta H is equal to C sub P delta T. And this only works for ideal gases, and it only works for constant specific heat problems. It only works for those. Okay? Now, people all the time forget which one. C sub V goes with U, or C sub P goes with U, or whatever goes on here. So let's think about this. The way I remember it is alphabetically. Look here. T, U, V. Okay, that's how I remember to use C sub V when I use delta U. Okay, and so whenever I see that, I can replace it. Now if you want to forget and you think, okay, what's the other one? Well, I remember our old friend Harry Potter. Harry Potter, who grew up in Britain, he likes to drink tea, so I write Harry Potter likes tea. That's my other one that I remember to figure out with delta H is C sub P delta T. But remember, these only works, and you can only use these two equations when you're dealing with an ideal gas with constant specific heats. Okay, that is very important. We're going to pause there, and then we'll continue on to our next topic.